When you plug an appliance into the wall, it is easy to picture electricity flowing through a simple, solid metal wire. But utility-scale power transmission cannot rely on a single monolithic element. To keep the grid alive, engineers must balance diametrically opposed physical forces. A power cable must carry massive amounts of electrical current with near-perfect efficiency, while remaining physically light enough to be suspended across miles of terrain or efficiently buried in trenches. It needs the mechanical rigidity to survive decades of environmental stress, yet it must continually manage the intense internal heat generated by the very electricity it carries. Because no known element can handle all of these demands at once, a completed distribution cable is a highly engineered composite structure, a frozen record of strict chemical and mechanical compromises. To understand how these structures actually work under load, we have to conceptually build one from the inside out. This process begins with the most fundamental component, the raw metal conductor that acts as the primary pathway for the electrons. Historically, mass-producing these continuous metallic cores required immense industrial effort. Factory workers had to manually manage heavy loops of raw rod, pulling the metal through dies to reach the exact diameter required for transmission. For over a century, the industry has relied heavily on two dominant metals to serve as this central pathway: copper and aluminum. The battle between these two specific elements sets the physical constraints for every subsequent layer we will add to the cable. Copper was the undisputed historical default for all types of insulated cables. It possesses excellent electrical conductivity and easily rolls into rods before being drawn into flexible wire. But in the late 1950s, the global price of raw copper soared, drastically altering the economics of large-scale grid expansion. This economic shock forced infrastructure engineers to adopt electrical conductor, or EC-grade, aluminum as a serious, large-scale alternative. The deciding metric was weight. Copper's density is 8,890 kilograms per cubic meter. Aluminum is 2,703. Equaling a copper block's mass requires vastly more aluminum. Despite lower mechanical strength, aluminum's electrical conductivity remains highly stable during stranding. Aluminum wasn't an untested theory at the time. British insulated cables successfully manufactured quantities of low-voltage, direct-current aluminum cables between 1909 and 1912. Some of these specific installations operated flawlessly until they were finally taken out of service in 1967. At the very center of the power grid, material selection is dictated exactly as much by global commodity pricing as it is by atomic properties. With the metal core established, we install an insulation layer to contain the electrical current and manage the extreme heat radiating outward. For decades, manufacturers relied on heavily processed natural insulators, wrapping conductors in layers of cellulose paper soaked in mineral oil or coating them in natural rubber. In the modern era, these natural materials have been replaced by synthetic polymers that provide highly specific, engineered thermal stability. How these polymers handle high-temperature loads comes down to a fundamental chemical divide: thermoplastics versus thermosets. Thermoplastics, like PVC, use long molecule chains held together by physical bonds. When temperature exceeds the melting point, these bonds break, and the plastic loses its structural rigidity. As it cools, the material hardens into a permanently deformed shape. To survive high-voltage transmission, engineers use thermosets like cross-linked polyethylene. It is treated to form permanent chemical bonds directly between the molecules. Because they are locked chemically, the material becomes infusible. Even under extreme thermal stress, the chains cannot detach. Chemically locking the molecular structure of the insulation is the only way to guarantee a high-voltage conductor will not melt its way out of its own casing during a thermal surge. Over the insulation goes the sheathing layer. This barrier is designed to keep environmental moisture out while structurally containing the internal components. Since the end of the 19th century, the heavy champion of the cable industry was lead. Lead is an exceptional moisture barrier, but it carries a severe physical penalty. At 11,370 kilograms per cubic meter, its extreme density makes it incredibly heavy to transport and install. Deploying legacy lines in extreme environments required significant manual labor to bend and maneuver the immense mass of the lead casing. Furthermore, successfully splicing and sealing these heavy lines in the field demanded highly specialized plumbing skills to ensure the joints were perfectly sealed without damaging the internal paper insulation. Over decades of use, large utility operators consistently ran into four main fault categories with lead: fatigue cracking from physical movement, manufacturing extrusion defects, fractures caused by internal gas pressure, and long-term chemical corrosion. While lead survived for generations, its inherent weight and structural vulnerabilities eventually forced engineers to transition to the lighter, more resilient synthetic polymer sheaths used today. The final, outermost layer of our distribution cable is the mechanical armor. This outer shell serves a dual function. It provides physical protection against external damage from shovels or rocks during installation, and it provides a highly conductive path to safely carry earth fault currents away from the system. Standard distribution cables are typically wrapped in mild steel tape between 0.5 and 0.8 millimeters thick and heavily coated in bitumen by the supplier to delay rust. If the installation environment requires higher tensile strength, such as in submarine cables or solid-type lines carrying over 11 kilovolts, engineers swap the flat tape for tightly wound galvanized steel wire. Alternating current induces a fluctuating magnetic field. Wrapping that field in steel creates inductive resistance, causing the armor to rapidly heat up. Swapping the magnetic steel for non-magnetic aluminum wire drops the inductive heating effect to zero. The exterior layer must block the physical environment from getting in, while simultaneously protecting the entire cable system from the violent magnetic fields generated by its own internal core. We now have a fully assembled modern distribution cable. Its aluminum core, chosen for economic conductivity, is locked firmly inside a high-heat XLPE thermoset. It is sealed within synthetic polymer sheaths to shed the crippling weight of historical lead, and finally wrapped in a protective cage of non-magnetic wire to neutralize AC induction. Advancements in synthetic chemistry allowed manufacturers to permanently phase out heavy, failure-prone natural materials like paper and mineral oil. When you look at the cross-section of a modern power cable, you are looking directly at a century of accumulated engineering solutions. Material science in infrastructure is not a quest to find one perfect, indestructible substance. It is the endless, precise management of physical, chemical, and economic trade-offs. And it is this exact balance of compromises, layered millimeter by millimeter, that ultimately keeps the modern world powered.